Hey everybody, welcome to the Chapter 14 Guided Problems. This is the first one, so why don't we just jump into it. It tells us that the accompanying data have a sample correlation coefficient rounded to 3 decimal places of negative 2.81. Perform a hypothesis test with the data to determine if the population correlation coefficient is less than 0 using an alpha of 0.1. All right, so in order to do this, well, the first thing we have to do is decide what our correct null and alternative hypotheses are. So whatever you're testing for, that's your alternative hypothesis. So it says to determine if the population correlation coefficient is less than 0. So that'll be our alternate hypothesis, that it's less than 0 here. So, and then our null would be the opposite, that it's greater than or equal to 0. So that's our first step. Next, we have to calculate the t-test statistic. So the formula for that statistic is on pages 657 and 658 in the book. It involves our sample correlation coefficient, which in this case is a negative 0.281, and n, which is the number of ordered pairs. In this case, we have 1, 2, 3, 4, 5 ordered pairs in this data set. Once we have that, we can calculate our t-test statistic. I'm just going to call it t-test. Using that formula, the formula is R divided by the square root of 1 minus R. 1 minus R squared, actually. So I'm going to go 1 minus R squared divided by n minus 2. N minus 2. So our t-test statistic, rounded to 2 decimal places, is negative looks like I have a problem here. It may not like the way I typed it, or I may have done something goofy. So rounded to decimal places. Make sure I did it right up here. So again, we're going to have R divided by the square root that might be it. Let's try that. All right, so let me just show you what I did wrong there, so maybe we can learn from it. I didn't have an extra parentheses here, so it made it look like I was just doing the square root of 1 minus R squared, and then dividing that by n minus 2, instead of saying the square root of the whole thing, which was the whole 1 minus R squared over n minus 2. So that was the error I made there. Hopefully you'll learn from my mistake. So now we have to have the p-value. Remember, a p-value is the probability that that a given x would be at least as extreme as the data value in question. So here we're going to use equals t dot dis, because we're using, this is the student's t distribution, because we just don't have enough data to do have to have a normal distribution. Our x will be our t-test. Our degrees of freedom will be n minus 2. And it's always n minus 2 when we're doing these regression problems. And then the cumulatives will be true. There's our p-value. I think it says rounded to 3 decimal places. 0.323. And then we have to do a conclusion. And this can get really confusing because it's easy to sort of talk yourself into it. So if I look at this, I say my probability here is a 0.3223. That's the probability of having a t-test statistic of negative 0.51. My alpha is only 0.1. So if my p-value is greater than my alpha, what that means is that I am not going to reject the null hypothesis because there's not enough evidence to conclude that our population correlation coefficient is less than 0. If our p-value had been less than the alpha, then we would reject it because we would have evidence that it was less than 0. That can be a little confusing. You have to kind of talk yourself through it. All right, and we'll go on to the next question. All right, here's question number 2. So this is consider the following set of ordered pairs, and then calculate the slope and y-intercept, the sum of squares total, the sum of squares regression, and the sum of squares error. So I'm going to show you how to do this using Excel. I'll try to make it super easy. So first thing we're going to do is export our data to Excel. And that'll bring it up. Just bring it up on my other screen here. So I'm going to drag it over. Whoops, it didn't like that. So I have to drag it over again. Make it a little bigger so it's easier to see. And now we have to use a tool in Excel, the data tool. It's called data analysis. And we choose regression from the data analysis tool pack and hit OK. First thing we have to do is tell it the Y range. So there's all of our Y data. Then our X range. And then we tell it where we want it to output to, which it's already actually guessed that, but sometimes it doesn't. And it gives us this output with like tons of information. So the information we're really interested in is this one right here and these three right here. So the first thing is this gives us our y-intercept and our x variable. And so our y-intercept is right here, 0.62857. It says 4 decimal places. So 0.6286. And then our slope, 1.114. Wait, 4 decimals, 43. Next, it's going to ask us for our total sum of squares. And so right here, so SS means sum of squares, and sum of squares total is 12.75. And then it wants our sum of squares error and our sum of squares regression. For some reason, Excel calls the error the residual. So our sum of squares error is 3 decimals places, 1.886. And our sum of squares regression is 10.864. And that's it. Of course, you can use the big formulas if you want to, but I thought you might like the way it does it in Excel. Okay, so here is the third problem, and I'm just going to warn you up front, this problem is horrific. It's like so fraught with chances to make mistakes and to not know where the mistakes are, and the question help stinks on it too. So I had to work through it a couple times to get comfortable with it, so hopefully this will be helpful to you, me working it out on here, and hopefully I don't screw it up. So it says, a part of a research program for a new cholesterol drug, as part of that research program, a pharmaceutical company would like to investigate the relationship between the ages of LDL cholesterol and LDL cholesterol of men. The accompanying data set shows the ages and LDL cholesterol levels of 7 randomly selected men. Construct a 95% prediction interval to estimate the LDL cholesterol of a 34-year-old man. So I'm going to go ahead and first things first here, open up our data set. I'll bring it over here so you can see it. I'll probably end up making this thing full screen because we don't really need that information anymore once we figure out a few points of data. So what makes this one hard is there's no real easy way to deal with it, and it's got a big giant formula. So I'm going to see if I can bring the formula in over here and see if I can paste it somewhere in my Excel spreadsheet just so you can see it. So that thing's nasty looking, right? Um, so, well, let's just take a look at it. Let's kind of break it down and look at all the different things we have here. So Excel won't do this for us. If we had PHStat, it would. So what we're trying to find is the prediction interval for a specific estimate of y, and they're calling that y hat. So here's the things we're going to need to work this formula. I'm just going through the formula. So the y hat plus or minus the critical t times, and that's the t alpha divided by 2, times the standard error, and then that's all multiplied by that big formula there. So that formula is going to need n, it's going to need x, it's going to need x bar, which is the mean of x, it's going to need the sum of x squared, and it's going to need the sum of x. So that's all the data we're going to need to sort of create a calculator to work this problem out. And it's not easy, okay? So don't get frustrated if it takes you more than one try. So now we can kind of go through this and figure out what we know right off the bat. So we know that our X, we want to find the LDL cholesterol for a 34-year-old man. Or actually, we want to find the prediction interval. So we know X is 34. We know N is the number of ordered pairs. 1, 2, 3, 4, 5, 6, 7. To find the sum of X, we'll just take the sum of all the X values. So that's 230. And to find the sum of X squared, we'll actually have to add a little column over here for X squared. That's just going to equal our X value, exponent 2. We can fill that down and then take the sum of it. That's the sum of X squared. X bar is just the average of X, so that'll equal average. And then these other pieces of information we're going to have to calculate. Our critical T for a 95% confidence interval, we can do that by doing T dot inverse. And then because it's a 95% prediction interval, but this is the T of the alpha divided by 2, okay? So our alpha in this case is 0.05. We divide that by 2, it makes it alpha is, 0.05. So if we divide by 2, it's 0.025. So to find our critical T, we're going to use 97.5, okay? And our degrees of freedom is n minus 2. So if n is 7, we can say n minus 2. Whoops. See, I already did something weird. Oh, 0.975. So there's our critical T. And then our y hat and our standard error, we're going to need to do some more work. So I'm going to go ahead and use the data tool. Click on data analysis, choose regression, hit OK. I want my Y input range to be Y, my X input range to be X, and I want my output range, we'll just put it right over here. So there's our regression output. So first of all, to find y hat, that's like saying what value of y will correspond with our x of 34. So if you remember the formula for a straight line, you learned it in school as y equals mx plus b, although the way they do it in this class is y equals b plus mx in essence, but it's the same thing. So the first thing we're going to do is we'll just figure it out. So y hat equals, so if it's y equals mx plus b, so our m is our x variable right here, and that's times our x. Should put those in parentheses. Plus b, which is our intercept. A good thing to do when you're doing this is to take a look at this number and see if it looks reasonable. So if we're saying for an x of up here, if an x is 32, it's about 196. If an x is 43, it's about 157. If an x is 36, it's about 177. So as our 34 of 170 seem reasonable, and it does. It's just a good thing to do to check. And then our standard error is actually, there's a formula in the book for it if you want to check it out. But our standard error is our SSE, or our sum of squares error. It's called residual in Excel. So it's the square root of that over n minus 2. So we're going to say this equals the square root of our sum of squares residual or error divided by n minus 2. So there's our standard error. So now once we have all of this data, we can be prepared to actually solve this problem. Now, you can do it how you want, but I find for me, if I try to do this all in a single piece, my chance of making an error is like 99%, it's super high. So what I do is I figure out the numerator. I'm just going to call it the numerator of this part of the equation. So the numerator equals x minus x bar squared. So there's the numerator of that little part. And then the denominator of that part, so this part right here, I just break it into these pieces so I have like a better chance of not screwing it up, I guess. This equals the sum of x squared minus the sum of x squared. So there's the sum of x squared divided by n. I'm going to add one more set of parentheses to make sure that the order of operations is correct. So that should represent our denominator. So now I'm going to solve the fraction there. I'm going to call it the whole part. And you can name it whatever you want. This is just my way of trying to keep it straight in my head. So that's the numerator over the denominator. And then I can solve for this whole square root part. and that's going to equal 1 plus 1 over n plus what I call whole here. And actually, it's the square root of all of that, right? Square root of 1 plus 1 over n plus this whole fraction we made right here. All right. So now we know that the prediction interval is going to equal our y hat plus or minus the critical t, or t alpha over 2, times the standard error times all of this stuff, which we figured out right here. So again, I'm going to go ahead and figure out my plus minus amount here. This is just my error, I guess we could call it, which is going to be my t alpha divided by 2 times my standard error times my whole part that was in the square root there. So now I can say my upper prediction limit equals my y hat plus my error. My lower prediction limit equals my y hat minus my error. And that should be my answer. Let's hope I didn't screw it up. I think it wants 1 decimal, so just to save me the trouble, I'll have Excel give me the answer in 1 decimal. So my upper prediction limit, 236.4, and my lower prediction limit, 103.6. You can see how there's so many chances to make an error in this. All right, so we got it right. So what I'm saying is, don't freak out if the first time you try this you get it wrong, because it's hard. I had to work through it a couple times just because there's so many little moving parts. You don't want to make an error. Again, this was my way of doing it to break down all of this information here. Someone who is more confident in their Excel skills than me, even though I've been doing it forever, but might just build this whole formula all in one thing, but I broke it down into parts. Anyway, good luck with it. You can do it, and well, we'll move on to the next one. All right, so here's our last problem. It's a little bit easier than the last one just because we can rely on Excel to do more of the work. So I'll open in Excel. And there it is. I'll make it a little bit bigger. Okay, so this is consider the following set of ordered pairs, assuming the regression equation is, it gives us the regression equation. Construct a 90% confidence interval for the slope. So we want to figure out how confident we are in that slope. Okay, so first thing we're going to do is run a regression. So we'll go to data, data analysis, click on regression, okay. Make sure it already guessed that this was my y data and that this is my x data, so that's good. And then my output, whoops. I think I messed something up. There we go. My output, we'll say to, all right. So this gives us all of the data we need. And so in order to solve this, the formula for the confidence interval for a slope is on page 681. But in essence, we need the slope, which they label as b sub 1. And we'll need the t alpha over 2, or the critical t. And we need the standard error of the slope, which is called s sub b. What's nice is that Excel kind of did this for us. So the slope is given to us right here. The critical t we'll have to figure out with t.inv. Remember, it's alpha over 2. So this has a 90% confidence interval, which means it has an alpha of 0.1. So alpha divided by 2 is 0.05, which would then give us 95% for the interval, and then degrees of freedom, which is n minus 2, which would be 4 for this problem. And then our standard error of the slope is actually given to us in this data right under standard error here. Let me make that wider so you can see it. So where it says standard error of the x variable, or which is the slope for this, is our standard error of the slope. All right, so to find our lower confidence limit, all we do is we take our slope minus the critical t times the standard error of the slope. Our upper confidence limit equals our slope plus our critical t times our standard error of the slope. There's our confidence limits. It asks us for 3 decimal places. So lower is negative 0.258 and upper is 0.724. And there you go. All right, well, like I said, number 3 is a toughie, so don't be afraid to use the video and slow it down and go through it step by step, and you'll get it. Don't worry. Good luck, and have a great rest of your day.